Okay, last time I taught this class, I had some questions about some of the steps we made previously. I didn't want to clutter the previous discussion with all of the steps, but I want to go back and make sure that each of these is clear and well justified. So, let's go back and look at the error analysis for just a minute. We have that our error term, A prime dagger E, is given using, oops, that didn't work out, using the SVD breakdown as before. Let's try this one more time. Copy, paste. There we are. And the question is, how are we going to analyze this? How did we go from here to coming up with the magnitude of A prime dagger E? So we did that above, but let's go through the steps. Recall that anytime we have this, that this can just be expressed in terms of the inner product. So our error squared then A prime dagger E squared is going to be the inner product of these terms. But this is going to get really difficult really quickly. So I'm going to, not difficult, just messy. Note that 1 over sigma is a scalar, and the inner product there is also a scalar. So we're going to define that as gamma r is equal to 1 over sigma r E with UR. So now that we have that defined, at least we won't have so many terms that we're dealing with. So we'll have gamma r, and we have our vector v r. That gamma comes from there. Okay, so inner products have these nice definitions that make them make it easy to, for example, pull out scalar terms. There's this VR with the sum R, gamma R, VR. And we can do the same thing here and pull that out, but let's go ahead and change our variable, our index variable, so we don't get the two r's mixed up because they're two separate things. And we can pull this out, gamma r, sum over k, gamma k. Now, if this is complex, then we're going to have a conjugate to deal with. But right now, we're just dealing with real quantities. And so we're okay. Now we know that that right there, and that should be a k. But that is equal to 1 for r equals k and 0 otherwise. for r not equal to k. So this whole expression then just comes down to sum over r gamma r squared, and we can substitute back in our definition for gamma, and so we get 1 over r, or sigma r squared, times the inner product of E with UR, and that quantity squared. Now, since we're dealing with real, it's going to be real, but sometimes people like to see that out there in front instead. Okay, so that's where the expression came from that we used up above right there. Let's see. Okay, one last thing before we move on to Tikhonov regularization. Actually, two things. Now that our aside is done, the first is, now we know that a dagger prime E squared is less than or equal to 1 over sigma r dagger, or r prime squared, times the norm of E squared. So if we've constrained the norm of E to be 1, then that's our limit. So if we have a very small singular value, we choose our r prime to be smaller to eliminate that one. And this puts a bound on the error that we can expect due to sigma r. Now the other thing that is important is assuming, as we've done before, that the entries in our vector E are normal IID then we really don't have to do this analysis again, because we've already done it. And the only thing that changes is we've now put r prime in place of r. And so we have here our expected noise error.